This is a practice run of Exceptional Ruby on Monday, January 31st, 2011. I'm Avdi Grimm, and I want to talk a little bit about error handling in Ruby. I have a few goals for this talk. I hope that by the end you'll have a better understanding of the mechanics of Ruby error handling. Hopefully you'll have a few new ideas about how to architect a robust failure handling strategy for your apps or libraries. And this is a fairly informationally dense talk, so if nothing else, by the end you'll be very, very bored. Let's start with definitions. What is a failure? An error? What is an exception? Are these all different terms for the same thing, or do they have distinct meanings? When defining these terms, it's useful to go back to the design by contract view of programming. In that view, every method has an implicit or explicit contract with its caller. It says, give me certain inputs, and I promise I will return certain outputs or cause certain side effects. So for instance, we know in active record, if we call the save bang method, the contract is so long as that record is valid, it will be saved to the database, otherwise an exception will be thrown. Failure occurs when code is unable to fulfill its contract. That could happen for a number of reasons. Mistake in usage, mistake in how the method is called, maybe a mistake in the implementation of the method, a bug. There could be a case that was not imagined by the programmer. For instance, a message type that wasn't expected. Or some element external to the program entirely could fail, like a web service returning a 500 error. The man who wrote the book literally on design by contract was Bertrand Meyer, and the language he designed, Eiffel, was also very influential on the Ruby exception handling system. He defined these terms like this. An exception is the occurrence of an abnormal condition during the execution of a software element. A failure is the inability of a software element to satisfy its purpose. An error is the presence in the software of some element not satisfying its specifications. Failures cause exceptions and are in general due to errors. I want to take you on a whirlwind tour of the life cycle of an exception in Ruby. It starts with raise. Every exception starts with a call to raise or fail. Raise and fail are synonyms in Ruby. They mean the exact same thing. They do the exact same thing. Which one you use is a matter of taste. These days I mostly see raise. I don't see fail as often in code. I was talking to Jim Weirich about this subject, and he mentioned an interesting convention that he uses. He uses primarily the fail keyword. He uses fail to indicate failures. He only uses raise when he is re-raising an exception. And this convention actually kind of makes sense to me. I'm thinking of using it in my own code. Alright, very quickly, a few of the ways you can call raise. Raise with no arguments is equivalent to calling it with a runtime error. Raise with a string is equivalent to calling it with a runtime error and that string. You can provide an explicit error class to raise an object of that class. You can raise with a custom backtrace to override the default backtrace. This is useful for methods like assertion methods, where you really don't want the backtrace to point back to the implementation of assert. You want it to point to where assert was called. Now, raise is a method on kernel, not a keyword. It's just a method, and of course that means, you know, where something is a method in Ruby, we can override it. Here's a simple kind of stupid example. If we wanted to make Ruby act like like older languages that didn't have exceptions and just crashed out when there was a failure, we could override raise to simply issue a warning and then exit with an error condition. Now, one note about overriding raise: you can override it in Ruby, and if raise is called in Ruby, it'll hit your override. But if it's called in a C extension, that won't see your override. A potentially more interesting use of the ability to override raise is a gem I wrote called Hammertime. Hammertime provides a Ruby error console. Whenever the program hits an exception raise, instead of just throwing it up the stack immediately, it presents you with a menu of options, including the ability to ignore it as if it never happened, to drop into a debugger, or to drop into an IRB session. So what does raise actually do? Raise essentially has 4 steps. First, it calls the exception method to get the exception. Second, it sets the backtrace. Third, it sets the global error value. And fourth, it throws the exception up the call stack. Let's go through those in detail. Step 1. You might think that when you look at it that raise calls .new on whatever exception class you pass it, and then passes the message to .new. But that's actually not what it does. What raise does is it calls the .exception method on whatever object you pass to it. Now, as it happens, the standard Ruby exception class implements .exception at both the class and the instance level. At the class level, it's equivalent to calling exception.new. At the instance level, if you call it with no arguments, it returns the exact same object. If you call it with arguments, it returns a copy of that object, but with new attributes set. This means that if we wanted to, we could write our own .exception methods on arbitrary objects and give them the ability to convert themselves into exceptions. It's almost like 2s is the standard method for converting to strings. .exception is the standard method for converting to exceptions, and this could be useful in, for instance, class hierarchies where we want to delegate which specific exception class is created down to the specific object. In this case, I'm showing an example of sticking an exception method on an HTTP response. And note then we can raise the response directly. We don't have to create an exception around it. Step 2 in raising is to set the backtrace on the newly created exception object. Step 3 is to set the global error variable. This is the $bang variable, but if that's a little bit too obscure for you, you can require English in your program, and then you can refer to it as error info. And what this little piece of code demonstrates is that the error variable has a value so long as there's an error currently active. In other words, while it's being raised and has not been handled, that's set. But once it's been handled, that variable is no longer set. Finally, raise throws the exception up the call stack, where it keeps unwinding the stack until it hits a rescue, an ensure, or it exits the program. Rescue is how we handle exceptions in Ruby. Rescue with no arguments will catch any exception, right? No. Rescue with no arguments will catch standard error, which means that there are quite a few exception classes that a blank rescue or a bare rescue will not catch. For instance, no memory errors, load errors, signal exceptions, interrupts, and there are others. You can call rescue with just a name and no class. It's equivalent to calling it with standard error. You can call rescue with a class. It'll catch all subclasses of that. You can also call it with a list of classes. Ensure is a good place to put code that cleans up your context. It's whatever is in the ensure block will always be called. Now there's an interesting edge case with ensure that was documented by Les Hill. If you raise an exception and then there is an ensure block in which there is an explicit return, then the method will return that value, and it will be as if the exception was never raised. So effectively, the exception is thrown away. This is probably something you shouldn't be doing. You probably shouldn't be calling explicit return in an ensure block, but it's a case to be aware of. Ruby is one of the few languages that provides a retry mechanism for exceptions. Retry throws the program back to the containing begin block, to the start of the begin block, and tries again whatever action caused the exception. Here's a classic example of using retry. We define a tries counter. We increment the counter every time we try the action. Whenever we rescue, we check the counter against some kind of threshold. If it's above the threshold, we give up. What happens if we raise another exception while handling an exception? Well, if we simply raise a new error, then the original exception will be thrown away, and the new error will be propagated. If you do this, there is no way to discover what the original failure was. And I've discovered several places where the Rails code does this, and I always discovered it the hard way. Please don't do this. It can be really frustrating to debug back to the source of an exception, only to realize that it was raised while handling some other exception, and you have no idea what that other exception was. Instead, use nested exceptions. Now, Ruby doesn't provide for nested exceptions out of the box, but it's very easy to define your own error class that supports them. And the idea of a nested exception is that it's just an exception that has a slot in it for an original exception, which was the one being handled when this exception was raised. While handling an exception, we can also re-raise with the same exception object. What this code demonstrates is that when you do that, it re-raises the exact same object. No new exception is created. We can re-raise the same object but with a new message. In that case, a new object is created. We can re-raise with the same object with an explicit message and a new backtrace, which both creates a new object and sets an explicit backtrace on that. We can re-raise with no arguments at all, and that's equivalent to calling raise with the global error variable, or in other words, with the active exception. Now, in some languages, raising twice like this, raising during exception handling, is frowned on or even disallowed. If we wanted to, we could use the ability to redefine raise in Ruby to mimic this, mimic the behavior of other languages. Here's an example where we redefine raise to check the global error value to see if there's currently an active exception. If there is an active exception already, it says no, you can't do that, and exits the program. And in this example, I've also defined an explicit error handled method, which unsets the global error variable, which will then enable us to raise a second exception without error, or without quitting the program, I should say. And here's an example of it in use. In this case, we are able to raise the second error because we explicitly called error handled. Ruby also gives us an else clause for our exception blocks. Else is the opposite of ensure. else is only called when no exception. I'm sorry, else is the opposite of rescue. It is only called when no exception was raised. What happens if an exception unrolls the whole stack and nothing handles it? Well, eventually the program will exit, but a few things are done before that happens. For one thing, Ruby has several ways to set code to be executed on the on program exit. I'm not going to go over the details of the differences between trap and add-exit and end, but suffice to say they are all called when the program ends. So if we raise an exception, they'll all be called. Or if we raise an unhandled exception, they'll all be called before the program ends. This is useful because it means if we have a program where for some reason it's impractical or impossible to put a begin, rescue, end block around the entire program, we can still define a crash logger that will catch unhandled exceptions and log some information about them, even though we weren't able to contain that whole program in a rescue. We can just define an @exit block, and in this example, the @exit block checks the global error value. If there's an active exception, it logs some information about it to a log file. It logs a timestamp, the error message, the error backtrace, and in this case it also logs all of the gems that were loaded, and the versions of the gems that were loaded when the error occurred. I'm sure you can think of lots of other things that would be useful to put in that kind of crash log. If an exception reaches the top level in a thread, it is held in that thread. The thread is dead, but the exception is held until another thread joins it, and then the exception is re-raised in the joining thread. The question is often asked, are exceptions slow? Simon Carletti did some research into this, found that the answer is yes. In both 187 and 191, an algorithm that used exceptions was about 37 times slower than an algorithm that avoided them. Does this mean you shouldn't use exceptions? No, as we'll talk about a bit more, exceptions should only be used in genuinely exceptional circumstances. So in general, it shouldn't be a problem that exceptions are so slow. Now when we handle an exception, we probably want to indicate the failure in some way. There are a lot of different ways that we could do this. We could simply return an error value. In Ruby, the most common error value is nil. Another way to handle a variation on this is to return some kind of benign value that will work for the caller, but doesn't represent real data. So here's an example of calling some kind of stock quote service, and if it was unavailable, we just dummy up some data. We might decide to put something out on the console to notify the user of the error, and we might use puts to do that. Now, puts really isn't well suited to this use for a number of reasons. Number one, standard out is buffered by default, which means that we might not see that message for a while, or it might come out in odd order compared to other messages. We could overcome that limitation by calling standard error.puts, which is written to standard error, which is unbuffered by default. But if we're going to put something to the standard error stream, we might as well call warn. Warn, like standard error.puts, puts the message to the error stream. and it's a bit shorter. But there is a bigger advantage to using warn. We all know that if we let spurious warnings grow unchecked in our program, it can hide real problems. So one day you might decide to get rid of all the spurious warnings that your program is generating, but it can be kind of tricky tracking down where they are all being, where all the warnings are coming from. But what you could do is you could, since warn is just another method on kernel, you could redefine warn temporarily to raise an exception, and now you have a handy tool that will pinpoint the source of every warning that your system is generating. In notifying the user of errors, you could go a step further and do some kind of remote failure reporting. You could log a message to a log somewhere. You could send an email. And then, of course, there are third-party services just for error reporting. Now, you need to be careful when you use one of these techniques, particularly something like sending an email or notifying an external service, that you don't make the problem worse. I worked on a system once where we had a subsystem that we had we created a very simple email error notifier for it. So if it failed, it would use our Gmail account to send us an email letting us know that it had failed. And this worked fine. But then one day we pushed out a software update that caused that subsystem to fail quite a lot. And suddenly it was generating these failure emails hundreds and thousands of times, and it was doing that using our Gmail account. And Gmail decided that it had started to behave like a spammer, and so it throttled us, which means that SMTP started returning failure values. Now, that error reporter had never been written to handle a failure from SMTP, and so that whole system started crashing because of the unexpected exceptions raised from the SMTP call. So now the systems were going down hard, and there was another problem. Now that Google was throttling our Gmail account, completely unrelated systems were trying to send emails and getting unexpected SMTP errors, and they too were crashing. So this is an example of the dreaded cascading failure. Failures are like rabbits. They have a habit of multiplying. If you have a few, suddenly you have quite a few more if you're not careful. One pattern that has been evolved to mitigate this circumstance is the circuit breaker pattern, which is described by Michael Nygaard in his book Release It, which I highly recommend. Circuit breaker is a mechanism in your code that has three states. It has the closed state, the open state, and the half-open state. In the closed state, your system operates normally, but an error counter keeps account of failures. Once the failure counter reaches a certain threshold, it trips the circuit breaker into the open position. And in the open position, your system is prevented from running anymore. So whatever it was doing that was failing, it's not permitted to keep doing it. Now, either after some timeout or after human intervention, the circuit breaker switches from the open position to the half-open position. And in the half-open position, the system is permitted to run again, but in kind of a zero-tolerance mode. The first time it has an error, it goes straight back to the open position and waits again for that timeout or that human intervention. And this is a great way to keep systems from getting into an error cascade state. And if you want to play around with it, somebody has put a Ruby implementation of the pattern up at this address. Some errors may be severe enough that you want to end the program, so you could, and to do that you could call exit with an error value like 1. Now, you should know that this doesn't immediately exit, it actually raises a new exception, raises a system exit exception. Now, if we're going to be outputting a warning and then raising system exit, we might as well use abort, because that does both in a more succinct way. If we really want to exit immediately without executing any of the exit handlers or doing any cleanup whatsoever, we can call exit bang with an error value. That finishes our tour of error handling in Ruby. Now I want to talk about somewhat higher level topics. I want to talk about structuring your failure handling strategy. And this is just, the rest of this talk is pretty much a random collection of tips and guidelines for how to raise and handle errors in your apps. Exceptions should not be expected. Exceptions really are intended for exceptional situations. As the practice of programming says, it is hardly exceptional to fail to open a file. Generating an exception in this case strikes us as over-engineering. Certain cases are not truly unusual and probably don't warrant an exception. Invalid user input generally isn't unusual, so active records save by default does not raise an exception on invalid input. The pragmatic programmers suggest a useful rule of thumb for raising. They say, ask yourself, if you remove all the exception handlers in the code, will it still run in the ideal case? If so, then good. If not, then you might be using some exceptions in non-exceptional circumstances. Your program shouldn't depend on exception handling in its normal state. If you do have a case where you want to unwind the stack several levels, but it's an expected case, not an exceptional case, Ruby provides a different mechanism. It provides the throw and catch mechanism just for that. And Sinatra is a good example of where that's useful. In Sinatra, you can call last modified at the top of an action to say to work with the browser and say, if the browser has the most recent version of this page, don't bother doing any other processing. Just bomb out immediately. And the implementation of that uses a throw to throw the halt symbol, and that halt is then caught farther up the chain in rack, and so you can it makes it very easy to just put a simple statement at the top of this method and prevent anything else from being executed in that case. So what constitutes a genuinely exceptional circumstance? Is an end of file a failure? What about a missing hash key? How about a 404 error from some external service? The answer for all these cases, of course, is it depends. It really depends on the situation. But by raising an exception, you force the issue. You say, I know. When you raise an exception, you say, I am certain that this is an exceptional condition. If if there's any doubt about whether the condition is truly exceptional, I say punt. And what I mean by that is to, if you can, to use a caller-defined failure strategy. And a great example of this is the fetch method in Ruby. Fetch is implemented by hash and by array and by some other standard collection classes in Ruby. And you pass it a key, and if a value exists at that key, then it returns the value. If the value doesn't exist at that key, it executes the block that you pass to it to determine what to do in that case. So you're effectively passing in your fallback strategy from the caller. So for an optional key, you could have a fallback strategy of just returning some default value. For a required key, you could have a fallback of raising an exception, and the caller decides. Another example is that uses a slightly different calling convention is the detect method on enumerables. In that case, since the block is already taken, you can pass a fallback in as an argument. I highly recommend using this pattern in your own code wherever you can. If there's ever any doubt over whether whether a certain condition really represents an exceptional case or not, punt the decision up to the caller. Now, the question of what is an exception and what isn't is kind of an internal question in software discussions. Many papers have been written about it, and articles, and there have been lots of arguments about it. And I can't say that I can give you the final word, but some people have asked me to suggest at least some guidelines for when to raise and when not to. So here's a few that I came up with. A few questions. It's basically 5 questions to ask yourself before you raise an exception in your code. Number 1, again, is the situation truly unexpected? If you're expecting a yes or a no answer and the user types Q, is that really unexpected? Probably not. Probably not a good place to be raising an exception. Number 2, realize that when you raise an exception, every time you raise an exception, you're potentially ending the program. Or at least if it's something like a Rails application, you are ending the request. It might be handled, but it might not be. Anytime you raise an exception, you could be causing the end of the program. So, ask yourself, is this condition worth ending the program over? Is it something that is so unhandleable and potentially fatal that it's worth ending the program or ending the request? Question number 3. Can I punt this decision up to the caller? Can I provide some way for the caller to push the decision down and maybe provide a sensible default instead of making the decision myself? Ask yourself, am I throwing away valuable diagnostics by raising this exception? If you've just produced a result from a really expensive 15-minute operation and then you raise an exception that throws all those results away in the process, it's probably not a good idea. You probably need to find some way of either passing those results back with the exception or getting to the end of the method without raising an exception. Another question to ask yourself: would continuing on in this case result in a less informative exception? So, would not raising an exception here cause some some weird second order, completely useless exception like can't convert nil into string. If that's the case, then maybe you do want to raise an exception. Maybe you want to raise it early while you still have an idea of what went wrong. As a rule, it's a good idea to isolate your exception handling code as much as possible. Exception code clutters up the flow of your programs. It clutters up the business logic with non-business logic, and it can become a readability nightmare. I've often come across pieces of code like this. This is a very cleaned up example, but I've often come across pieces of code that had nested begin within nested begin, and invariably they were some of the hardest to test, hardest to understand, and buggiest parts of the code base. I would go so far as to say that that in Ruby the begin keyword is a code smell. And remember, a code smell doesn't mean it's always bad. It means it's a possible alarm. But how do we avoid begin statements? Well, Ruby actually gives us a really elegant idiom that enables us to get by without ever having a single begin statement. If you have a single rescue block at the top level of a method, you can get away without the begin statement. And when you do this, you have this really neat delineation in your method between business logic in the top half of the method and error handling at the bottom half of the method. And I find that when you structure your code so that all of your methods look like this, they only have a single top level rescue delineating between mainline logic and error handling logic, it leads to better factored code and more easily testable code. One way to refactor code that uses begin blocks into this idiom is to use guard methods. So if right in the middle of your business logic you have this case that you have something raises an IO error and you have to handle it if it happens, you can extract that out into a guard method whose only job is to handle that error. Certain methods in your programs and libraries are critical. Particularly methods that are called while handling errors. You really want those to be bug-free, and you want to have a good understanding of how they operate and know that they operate reliably. Also, anything where you have a resource that needs to be cleaned up, you really want to know that that method will behave well in the presence of exceptions. Now there's a set of guarantees that can be stated about a method, and I think these were first enunciated, at least as far as I know, they were first enunciated in the C++ community, but they are equally applicable to the Ruby community, and they're just there's something to think about as you implement a particularly critical method. What exception guarantee does this method make? And the three guarantees are: the weak guarantee says simply that the object will be left in a consistent state. So, for instance, it won't have any dangling references to objects that don't exist, or like IDs of active records that don't exist anymore. So things like that. The strong guarantee says that the object will be rolled back to its beginning state, so it'll either succeed or it'll go back to as if it was never called in the first place. And then the strongest guarantee is the no-throw guarantee, which says that no exceptions will come out of this method. When can an exception be raised in Ruby? Given this code here, what parts of this code could potentially raise exceptions? Well, it's a trick question, because the truth is Ruby makes no guarantees about when an exception might be raised, and there are several exceptions that could be raised at any point in your program. For instance, if you run out of memory, the no memory error could pop up anywhere. If somebody hits Control-C, that signal exception could pop up anywhere. You have no guarantees. So we know that it's good to make certain exception safety assertions about critical methods, and we also know that in Ruby you can never tell when an exception will crop up. So how can we say for sure that that a method will behave the way we think it will in the face of exceptions? Well, there's an old method called, as far as I know, just exception testing for determining whether a method actually lives up to its exception safety guarantees. And there are a few elements in exception testing. You have a test script, something that puts the method through its paces. You have some assertion about its behavior when exceptions are thrown. So, for instance, an assertion that says that it supports the strong guarantee, where it will be either succeed or be rolled back. And then you have a record phase and a playback phase. I'm gonna step through this. So here's for instance, here's some code under test. Here's a classic little piece of code that just swaps two keys in a hash. In the record phase of our exception tester, we create a hash. We pass the test script. The test script in this case is a call to swap keys that says swap keys A and B. And in the record phase, we execute that code and we record every external call that's made by that code. So in this case, it records 4 call points, which are all calls to hash methods. And then in the playback phase, we make an assertion. Here we're making the strong assertion. We're saying that either the keys are fully swapped or they're not swapped at all, but they're not stuck in some intermediate position. And our exception tester is going to run the test script as many times as there are call points, and each time it's going to pick a different call point and force that call point to raise an exception. So in this example here, it's reached the 3rd call point, and it's forcing that hash call to raise an exception. And then what it's going to do is it's going to catch that exception and verify that the assertion still holds. Now, this is actually pretty straightforward. This kind of tester is pretty straightforward to implement in Ruby. I didn't have space to show the implementation in these slides, but there will be a link to the example code at the end of the presentation. Here's an epiphany that was useful to me in thinking about exception handling and safety guarantees. Consistency and validity are 2 different things, and it took me a while to realize this. When we say that a method will guarantee that the object stays in a consistent state, that's not necessarily saying that it stays in a valid state. So validity says, are the business rules for the data met? Consistency just says, can the object operate without crashing or exhibiting undefined behavior? I thought I'd pass this on because it helped me to think about the problem when I realized that these really are 2 different things. Here's another little piece of advice. Be specific when eating exceptions. Every now and then you have an exception that you know you don't care about, and so you catch it and you throw it away. That's fine. But when you are excessively vague in specifying which exception that you're catching and throwing away, invariably you get some unexpected exception eaten and thrown away, something that you really did want to be propagated up the chain, and somebody beats their head against the wall for a while trying to figure out what's going wrong with the code because they don't realize an exception is being thrown away. If the code is throwing, if this exception that you're throwing away is some generic exception class like runtime error, at least try to, in that case, you can at least filter on the exception message instead of just catching all runtime errors. You should try to raise consistent with your abstraction level. If you have a method that returns the local temperature based on some web service or something, it probably shouldn't be returning an IO or raising an IO error. It should be raising something higher level than that. It's a good idea to define your own error-based class, and all the errors that you raise can be errors that derive from that. This is a good place to put your exception nesting mechanism that we talked about earlier. It's particularly important in libraries. When I was talking to people about what to include in this talk, a bunch of different people said please don't let your libraries raise any old random exception. Let every exception that comes out of your library be an exception that's derived from a single library specific exception class. So I guess there are a lot of people out there that have been burned by having random unexpected exceptions come out of libraries. And if you want to do this, if you want to make sure that you comply with this rule, one thing you can do is just at the top level calls in your library, you can have clauses like this that catch any non-library exceptions and wrap them in a library exception. When you're structuring your exception hierarchy in an app or a library, there are a lot of ways you can go about it. You could do it by module. If you've got different logical modules, you could have different errors for each one. You could have a different type of exception for each layer of the software, high to low. You could even have different exceptions for different levels of severity. It can be really difficult when you're looking at an app or a library at the beginning to figure out the most useful way to structure your exception hierarchy. What I like to do is to actually work backwards. The only reason we create different exception classes at all, the only reason we don't just raise runtime error for everything, is because we want to be able to easily differentiate between exceptions so as to handle them differently. So I think it's a good idea to look, when deciding which classes to make, to look at the different ways that errors are handled and then work backwards from there. So for instance, some standard error types in a web application, or rather some standard ways that they are handled as seen by the user, are these. There's the user error that says that you did something wrong, you need to do something different. Another error that you commonly see in web apps is the logic error. That's the one that says something has gone wrong, and we've been informed and are working on it. In other words, there was a bug in the system, some unexpected thing happened. There's nothing you can do about it except wait for us to fix it. And then there are transient errors, and those are generally reported differently from user errors and logic errors. Transient errors indicate that it wasn't a bug, but there's some service that's unavailable right now, and so it's not able to service the request. So if we work backwards from those three different ways of presenting the problem to the user, we wind up with three essential exception classes that I think will cover 80 or 90% of the cases that that you have in most programs. You have your user error, your logic error, and your transient error. And now if you're implementing a library, you might want to break logic error down into internal error and client error. They'll both probably be presented to the user the same way, but they'll give you a way to give your library clients a way to differentiate between something they did wrong and something that broke inside the library. I thought of trying to reduce all of this to a set of bullet points to sum it all up at the end, but I couldn't begin to do that. So no recap, but hopefully you got something useful out of this presentation. Thank you very much for listening, and I will be putting, I referenced a lot of books, a lot of articles, and other bits of software in this talk. I will put references to all that stuff at this URL.